Okay, we're going to get started tonight. Welcome. Hope everyone enjoyed their dinner virtually. My name is Russ Preuss. I'm the Delaware Valley Geo-Institute Chair. I work at Gannett Plumbing, for those of you that don't know me. We're expecting over 100 or maybe 120 attendees tonight, which is excellent. I mean, normally on a given night we were getting 60 or 70 people, so we have over 100 tonight, which is excellent. I hope everyone is staying safe during these uncertain times. Before we get started with the presentation, I would like to make some announcements for the DVGI. Our next planned meeting or scheduled meeting is in September, so this is the last meeting for the year. We are planning to do a seismic update to the 2018 IBC in September. Hopefully conditions with COVID have improved by then, and we can do an in-person meeting. We have Zia Safar from Kleinfelder scheduled to do the presentation that night. And unfortunately, we had to reschedule our golf outing, which was supposed to be in June. We're looking to hopefully do it in the fall, but stay tuned for that. And final announcement, we have the DVGI Project of the Year competition going on. This is the inaugural edition. Many of you have seen this. We've been outlining these in our monthly newsletters. So these 4 projects have been submitted. The I-95 test section by STV, the Penn First Pavilion by Pierce Engineering, and the SR-209 Rock Slope Mitigation Project by Gannett Plumbing, and the Jaeger Airport Runway 5 by Chernobyl. So these were submitted and carefully evaluated by our board, and we have made the selection. Unfortunately, we wanted to do this award in person, but we figured it's do it tonight. And here we go, drum roll. The project of the year goes to the Penn First Pavilion by Pierce Engineering. So congratulations to Pierce Engineering. As part of winning the award, we want to be contacting you hopefully about giving a presentation on this amazing project, maybe in the fall. And also we're going to give you an article, publish an article in the National Geostrata magazine. So congratulations again to Pierce Engineering, and thanks to all the other candidates too. The projects were excellent. It was a tough decision to make for our board. We hope to do it again next year. On to tonight's meeting. Tonight is the traveling lecture. We are fortunate to be selected. DVGI was fortunate to be selected for the annual lecture program by DFI. I wanted to first of all, thank DFI for their assistance in organizing the meeting, mainly Mary Ellen Large, Jamie Satina, and Katie Scully. Were very helpful in organizing the meeting and setting up the WebEx. We were supposed to have it in person, but we were able to still have the meeting tonight. We're thankful for that. Couple notes on the presentation. Everyone knows everyone's going to be on mute. If you have any questions about presentation, please do that in the online app on the questions. So I'll be monitoring that. I'll take a look at that. We'll have probably a stop mid-presentation for some questions, and also at the end. So please feel free to ask questions. We'll have time to discuss. DFI is going to be providing PDHs for tonight, but just please be patient. Allow a couple weeks to receive an email with your certificate. So I want to get on to our presenter. It's Mr. Willie NeSmith from Georgia. Unfortunately, he was supposed to come up and enjoy Philadelphia, but now he's I'm sure he's at his home right now. But Willie is a former chief geotechnical engineer for Berkel Company Contractors. Willie received his BS in civil engineering from the Georgia Institute of Technology. He's an expert in the design and installation of cast-in-place displacement piles. He's designed or evaluated over 200 displacement pile projects in the United States over his 45-year career. His presentation tonight is titled Drilled Shaft Displacement Pile Performance at a Site with Coastal Plain Overlying Residual Soil. And at this point, I would like to welcome Willie and turn over the mic to Willie. Thank you.
Thanks very much, Russ. I appreciate it. That was a very nice introduction, but you left off a critical part of my title, and that is emeritus. And through the years, I have met people who had that title, and I always thought it sounded very impressive. And when it was applied to me, I got someone with a background in Latin to help me understand what it meant. And they told me basically it means an old person who is not paid. So there you have it. That's the emeritus part. I am coming to you from Georgia, actually South Georgia. I live about 40 minutes from downtown Savannah. It's a fairly rural area, and there are a lot of good old boys around here. And when this COVID-19 thing got started, the word around the campfire was that if you consumed a significant amount of alcohol, that you could stave off the virus or at least mitigate its effects. And later that approach has been debunked, I think, by the science, but I'm sticking with it because it's worked well for me so far, and yeah, I'm going to hang in there. Tonight's presentation, as Russ mentioned, is part of the traveling lecture series presented by the Deep Foundations Institute. And it occurred to me, I don't know, a couple of months ago, I was giving a presentation at a large university, and I mentioned the DFI, and I asked, there were about, I don't know, 40 graduate and PhD students in the audience, as well as several professors, and I asked if they were familiar with DFI, and no one raised their hand. And I thought that was odd, but then afterwards I thought back on my own career. I began, I graduated just about the time that the DFI was founded. That was in 1976, and I was doing graduate work at that time. Went to work for a consulting engineer, and really didn't hear much about the DFI for a long time. And as my career evolved, I started doing, somehow drifted into doing work for deep foundation contractors, and began to get a sense of what the DFI was and what they began to do, what they did. And then in the late 90s, I went to work for Berkel Company and became very involved in the Deep Foundation Institute. So at this point, the DFI is part of my history, and the participation in DFI is just something that just comes normal to me. But thinking back on it, it was not something that was in the front of my consciousness during my time as a consulting engineer. But the mission statement that's on the screen now, I think, is the essence of what the DFI tries to do. And that is to bring together the people that are involved in the design and execution of geo construction and help them find common ground, which I think is a terribly clever catchphrase, if you will. The organization itself is made up of about a third of the members are contractors, roughly 25% consulting engineers, and then suppliers, an academic component, and some owners. And it's really a great place to be able to sit with basically everyone who's going to be involved in a project from the design through the execution standpoint and discuss items of mutual interest. And I found it's a much better place to have a discussion about even the testy items rather than waiting until they occur on the project site. So DFI has been a very important part of my career, and I would hope that you would check out the DFI, see what it has to offer if you're not already familiar with it. Up on the screen now are the technical committees and working groups associated with the DFI. When I got involved, it was not nearly this large, but basically anyone who has an interest in any facet of geo construction would find a committee here that that they could get involved with. And I certainly hope you will visit dfi.org and see if there's something there for you. As far as upcoming DFI events, this international conference on piling and ground improvement was originally scheduled for the fall of this year. That has been rescheduled for spring of next year. Superpile 20 is going to be presented as a virtual event, and this particular event is one of my favorites. There is a treasure trove of information, again, from a design and a construction and evaluation standpoint, presented in these Superpile events. Unfortunately, the Deep Mixing Conference in Gdansk, which was originally scheduled for this summer, has been set back to 2021. Slopes, slides, and stabilization is going to be a virtual event in August. It looks like the Frontiers and Offshore Geotechnics is still scheduled as a live event in Austin in August. And then the annual conference is still on as a live event in National Harbor, Maryland. So these are just some of the things that are upcoming with the DFI. And again, go to dfi.org and see if there's something there for you. Tonight's presentation is the evaluation of cast in place piling in intermediate geomaterials. And the presentation is going to just take a general look at the evolution of the piling equipment and processes, the definition of intermediate geomaterials, and then a couple of example applications for this process. From a historical perspective standpoint, just a brief review of how auger cast in place piles came to be. They grew out of the pressure grouting process at a company called Intrusion Prepack. And in the late 1940s, this company was well known, did work all over the country, and their primary way of establishing foundations was to grout pre-placed aggregate. So they would typically place some aggregate and then auger down or drive a grout probe down to the desired depth and start grouting and then extract the probe. Occasionally, they would have to use an auger in order to get down to the level where they needed to be, and they did this not only with pre-placed grout, but with just grouting processes in general. So they would extend an auger down, drive a grout pipe beside it, and then pump grout and remove the auger at the same time. And somewhere along the line, and I never got a straight answer from anyone about how it happened, but somebody decided that, hey, we could actually build a cast in place pile like this. And to my surprise, many significant structures in the Midwestern United States were constructed using this process, and that is augering down and driving a grout pipe beside the auger, and then pumping grout and removing as the auger was removed. Eventually, a system was devised by which the grout could be pumped through a hollow stem in the augers, and that eliminated the separate grout pipe. And licenses were granted. A patent was received by, was given to Raymond Patterson of Intrusion Prepack. And then later, in the late 50s, licenses were granted to Lee Trezillo and Charles Berkel for the installation of cast in place piles. In the early 1960s, the augers were advanced by power units that developed, that were, by today's standard, were fairly anemic, 15,000 foot-pounds of torque. The grout that was used in the auger cast piles was batched using bag cement and fly ash and a grouting agent and masonry sand, much like you would see a masonry project being done today. That was the way the grout was. That was the way the grout was batched, and obviously using that kind of processes and those materials, it was difficult to produce a consistent 3,000 psi grout, and the installation of, say, 500 linear feet of piling in a single day was considered a significant accomplishment. In the 1960s, most of the deep foundations in the larger urban areas were either driven piles or drilled shafts. The driven pile side of the equation was largely controlled by either wooden piles, precast concrete piles, or Raymond concrete piles or Raymond step tapered piles at that time in the 1960s was a significant force in the deep foundations industry. By the 1970s, the augercast community had advanced in terms of the materials that were used and the equipment that was used to advance the augers. They were now up to the 30,000 foot-pound range. They had started using ASTM C33 sand in the grout mixes, which made it much more pumpable. There were higher volume, more powerful pumps available. Ready mix producers were now supplying a large amount of the grout that was used in these processes. And the original patent for cast in place piles expired, and a large number of new installers began to enter the market. Looking at one urban area and the way foundations were approached in that area, and that is Atlanta, which lies in the Piedmont province. Again, you have Raymond step taper piles, which were normally driven through the residuum and seized up usually somewhere in the partially weathered rock, perhaps down on intact rock. Structures of significant size were normally placed on caissons, which were drilled through the residuum into the underlying rock to bear on intact rock. At that time, auger cast in place piles normally stopped near the top of the partially weathered rock. So all the shaft resistance they got was pretty much in the residual soil. All of that sort of changed as we moved into the 1980s. At that point, auger cast piles were pretty well known in the geotechnical community, and there was a continued advancement of the installation platforms and the grout delivery systems that led to application in a wider variety of geologic settings, and also the application in intermediate geomaterials. And there are two projects that really were pivotal in the 1980s in terms of the development of auger cast in place piles. One of those was the Miami Rapid Transit System, which were piles that were installed into soft limestone, and the Georgia World Congress Center in Atlanta, which were piles installed into partially weathered rock. Both of these projects, on both of these projects, conventional crane mounted auger cast in place pile tooling and processes were used. At that time, the basic tooling was a set of leads, an auger, a grout pump, all hung from a crawler crane with swinging leads. And this is a photograph of a typical piece of equipment on the right. That was the standard way auger cast in place piles were installed, even into these intermediate geomaterials in the 1980s. And just another photo of a fairly large auger cast in place piling system that was used. In the early 90s, fixed mast platforms began to enter the scene, and they were, at least initially, primarily used for the installation of displacement piles, but very quickly got adapted for the installation of conventional auger piles. The fixed mast rigs, like the one shown here, were capable of developing significantly higher torque than the crane mounted systems that were being used at that time. These installation platforms came from Europe, and because of the way the European piling systems were installed, there was a great deal of emphasis on gathering information during the drilling process. So there was a rotation proximity sensor, a main winch proximity sensor, an inclinometer that points to the tooling. The actual inclinometer is in the mast, and then a way to monitor the hydraulic fluid pressure of motors that were driving the turntables. So this installation platform, again, which was primarily imported from Europe, would allowed a whole different set of parameters than the conventional crane mounted platforms. This particular photograph was taken at a site in Los Angeles County that was the redevelopment of the old Howard Hughes Airport area. And because it was the first cast in place pile system in Los Angeles County, we were required to extract a pile so that the building officials could look at it. And there it is. It took a significant amount of effort to get that pile out of the ground, and all the water you see is a result of the jetting that had to be done to get it out of the ground. Once it was out of the ground, it was kind of instructive, though, because you can see the material that was adjacent to the pile that's actually adhering to the pile, and it points out clearly one of the advantages of cast in place piles, and that is there is not a smooth interface between the pile and the soil. The pile actually becomes integrated into the soil. And in this case, the upper part of the profile was a silty fine sand. The lower, approximately 3 feet, was a coarse sand and gravel, and you can see that material adhered to the pile. Again, these installation platforms had torque capacities much higher than conventional auger cast in place piles. These platforms are being improved almost daily. So the installation platforms that's shown here is capable of producing 150,000 to 200,000 foot-pounds of torque. And a key element related to conventional auger piles mounted on crawler cranes is that they had the ability to exert a downward force or crowd on the tooling of 40 to 80,000 plus pounds. So a significant change in the from the conventional crawler crane mounted operations. Again, these systems came from Europe, and they had a extensive data acquisition system associated with them, the ability to record time, depth, hydraulic fluid pressure, and rotations. And again, all of that was related back to the way cast in place piles were installed in Europe. The reason for going through the fixed mast systems is that for any given project where there is a consideration of going into intermediate geomaterials or very hard materials, there may be a consideration for using a fixed mast system as opposed to a crawler crane mounted system, simply because of the ability to exert crowd and in general turntables that develop significantly higher torques. With respect to that, there's some logistics consideration that need to be brought to mind. On the left is a conventional fixed mast piling system. There's the turntable, the fixed mast. As you can see, this rig has to be able to get to within about 6 feet of the piling location. On the right is a crawler crane mounted system, what we would think of as a more conventional piling system, which can sit over here and reach out 30 feet or more to reach a pile location. So if you're looking at a project that you're concerned about being able to penetrate, and you think, okay, we need a fixed mast system for this because of the higher torque and the crowd, you may now also need to consider the logistics on the site of simply being able to get the tooling to the piling location. This is just a comparison of the tooling for a conventional auger cast in place pile rig, API flighting at a fairly narrow, small stem versus a fixed mast system where the stem necessarily has to be able to handle much higher torque than the conventional auger cast in place piling system. I just wanted to pause for a minute, Russ, and see if there are any questions up until this point. The slide on the screen references the online documents that are available through the DFI. And again, it is a treasure trove of information. If you want to get into it and look at projects from the standpoint usually of the design, installation, and evaluation of deep foundations. Do we have anything, Russ, at this point?
Hi, Willie. No, we don't have any questions as of yet.
Fair enough. We push on.
Sure.
So, intermediate geomaterials. What are intermediate geomaterials? Well, we look to the Department of Transportation for their description, and they describe cohesive soils, granular soils, and then I've skipped down to to rock. So intermediate geomaterials are, they divided up into cohesive and non-cohesive materials, but they're basically cohesive materials, clay shales or mudstones with an undrained shear strength of 2.5 to 25 TSF. Cohesionless materials, granular tills, granular residual soils with an N value in excess of 50 blows per foot. And I have found it useful to look at these materials in terms of this chart that was developed by Kohawi and Foon in 1993. I know that's old, but I still use it. I still use it quite a bit, and it looks at unit side resistance for piles and drill shafts versus undrained shear strength. And along this line, there are the typical soil type materials. And then along this disconnected line, there are rock-like materials. And what we are talking about tonight are installation into the materials that would lie sort of in this area. The intermediate geomaterials, as is the term that I'm using, that they're basically on the soft end of the rock or hard end of the soil scale. Types of intermediate geomaterials would include materials that were on their way to becoming rock but were not fully indurated to the point that they could be called rock or classified as rock. Soft limestone, mudstone, clay shales. Secondly, materials that were once rock but have been weathered to the point that they've lost some of their rock characteristics. And those are residual soils, residual materials, partially weathered rock or altered rock as they are called. I think it's important to point out that these residual materials, the less they have been weathered, the more they retain some of the characteristics of the parent rock. And one of those characteristics is that they can have a significant amount of the strength of the parent rock, which again leads to a higher load development. The third material is those that have been acted upon by physical or physiochemical processes that cause them to meet the criteria for intermediate geomaterials, and that would be tills or marls. A common feature of many intermediate geomaterials is the difficulty in obtaining boring data and samples that accurately reflect the in situ characteristics of the mass. They are quite often too hard to be sampled effectively by conventional soil test boring methods, but too soft to be sampled by conventional rock coring processes. That is not universally true, but it is true among a large number of the intermediate geomaterials. The partially weathered rock or altered rock in the Piedmont is an excellent example of the intermediate geomaterials. And the slide that I showed previously for the 1970s showed the auger cast in place piles stopping at the top of partially weathered rock, and that was because they simply didn't have the means to penetrate into the partially weathered rock. Beginning in the 1980s with those projects that I mentioned, the Georgia World Trade Center and the Miami Rapid Transit System, auger cast in place piles were able to penetrate these intermediate geomaterials. And in the case of the Piedmont, we're able to get into partially weathered rock and basically go down to refusal, which would be considered intact rock. So why go to the trouble of getting down to through the partially weathered rock or into the partially weathered rock? And I've attempted to illustrate that here with a profile in, and I wouldn't call it I don't know if there is a typical Piedmont profile, but this is a profile from the Piedmont province, and it shows standard penetration resistances, except for this blip up top, generally around 10 blows per foot, and then increasing up into the 20s, and then going up to the intermediate geomaterial range, which is 100 blows per foot in many cases. If you look at the available slide resistance in auger cast in place piles through the residuum, which up until the 1980s was all the auger cast in place piles could do, you're looking at 0.75 to 1 TSF. Once you get into the partially weathered rock, the intermediate geomaterial, that shaft resistance goes to somewhere in the range of 2.5 TSF. So basically, by being able to penetrate into this zone, you can develop roughly 2.5 times the shaft resistance. So that is the appeal of being able to get into the partially weathered rock or the intermediate geomaterial zone. To look at a local project, local to you in Philadelphia, there was a project, it was called by Berkel 500 Walnut Street. It was at the intersection of Walnut and 5th. And you can see that it, on this plot, it lies across a part of Dock Creek. Well, apparently Dock Creek, or this portion of Dock Creek, was filled in the 1750s or so. So anyway, this is where the project was located. The profile in the project was the urban fill. I know that covers a large territory, and when you operate primarily in the southern United States and then start to do projects in New York and Philadelphia and other areas that have a much longer history, urban fill can mean something quite different. But In this case, there was an excavation to the building basement level that penetrated pretty much through the urban fill material. So what we have from a profile standpoint is fluvial soils down to a total depth of approaching 45 feet, about 42 feet. And this was apparently material that was associated with the original Dock Creek. I guess it was a sort of a marshland sort of area, clayey silty clay, some seams of sand, very erratic penetration resistances, weight a hammer to 14 blow material. At about 42 feet, we get into some alluvial soil that's a little bit more consistent in terms of the material type. It's a coarse sand, sometimes with a significant amount of silt and gravel. The penetration resistance is from 4 to 40 blows per foot, and the average was about 25. Then we get into a very high consistency granular zone. I'm sure known to you as the Trenton gravel, which in this case had an average penetration resistance of 70 blows per foot. I don't know that the Trenton gravel qualifies as an intermediate geomaterial from the standpoint of the definition that I've given here, but it certainly is capable of producing some significant shaft resistance in cast in place pile. And underlying the Trenton gravel was some decomposed or altered or weathered rock, which is the intermediate geomaterial that was the basis of this, which is what this discussion is about. Generally, standard penetration resistance is in excess of 100 blows per foot, where you can recover a rock core. It was the RQD is less than 40, and then the idea was to extend these piles down to refusal so that they sat on intact rock. From the load test that was run there, the implied load transfer in the bottom 14 feet of this test pile was about 2.65 tons per square foot. And that sort of fits right in with the area that we've been discussing, the intermediate geomaterials, which would be, again, between the very hard soil and the very hard rock, the very soft rock range. This is the load test from that project. 18-inch auger cast in place pile. It was the design target was a compressive capacity of 200 tons. You can see it was loaded to 500 tons. Was not showing any sign of failure at that point, but that was the capacity to which it was loaded. This is a tension test that was run on that material. So again, by being able to penetrate into the intermediate geomaterials, the partially weathered or altered rock, and sit on relatively unweathered rock, we were able to develop some very significant capacities for this project. Initially, it was designed for drill shafts to go down to rock, but the site configuration, given the basement and the site configuration, drill shafts would not have been, would have been a real problem to install drill shafts at this site. Another area where a significant amount of work has been done, and I referenced the Miami Rapid Transit project that was done in the 1980s. In the Miami area, there are these alternating zones of oolitic limestone and sand. And as it turns out, the deeper you go, the more higher consistency the oolitic limestone becomes. But it's still in that intermediate geomaterial range because it's very, very difficult to get an intact sample to do an unconfined compressive test on. But this is because of the early success of the auger cast in place piles in the Miami Rapid Transit system and the tremendous growth of Miami. Auger cast in place piles have become a sort of the go-to system in the Miami area. And I'm putting this forward just to show how information is developed in an area where there are a large number of projects and a large amount of information to be had. In this case, if you look across the x-axis there, this is unconfined compressive strength, and this is the upper Miami limestone. So we're looking at unconfined compressive strengths in generally in the 10 to 15 ton per square foot range, and shaft resistances in the 2 to 4 tons per square foot range. As you move into the deeper Fort Thompson limestone, then you're looking at where unconfined compressive strength samples can be obtained in the 35 to 40 tons per square foot range, and side shear values of 8 to 10 tons per square foot. So kind of moving up the food chain in terms of the kind of shaft resistance that can be developed. If we go back to the Cohaue and Foon chart, now we're operating pretty much with the oolitic limestone or the Miami limestone at the lower end of the rock range. Recall that with partially weathered rock, we were in the 2 to 2.5 tons per square foot range. With the Miami limestone, we've moved up significantly from there, again, into the this soft rock range. This was part of the paper that was published with the other information that I've shown you, and to me it points out the difficulty in getting a reasonable sample or a reasonable feel for what an intermediate geomaterial looks like. And I don't know how they ever did a linear regression on this, but again, to me, it just points out that when you're dealing with intermediate geomaterials, really tough to get standard penetration test results, samples that are meaningful, also difficult to get an intact core sample of the material to get unconfined compressive strengths. Just a couple of photos from that project, and I wanted to point out this is a conventional crane mounted auger cast in place pile rig. That turntable is a conventional one, but the contractor in this case got a little cute, and that turntable is one that was extracted from one of the European fixed mast rigs, which could develop significantly higher torque than that one. So you got to give it to the contractors. They're always out there thinking and looking at how they can do things better. Just a shot of that, the turntable and the rig and the kind of material that's coming out. It's pretty much, it's quite often a white dust, or if you reach down and grab a handful of this, it would be just some chalky looking gravel. But again, capable of developing some significant side resistance. Just an example of a contractor's made device for getting into intermediate geomaterials. Again, they're always out there thinking about how they can do things better and faster and cheaper. And again, this is something that was fabricated in a contractor's shop in order to penetrate intermediate geomaterials. Shale is one of the materials that I mentioned in the initial discussion, and it is it's a little bit different than the other material. I've put here highly dependent on local geology. Well, all of the materials are, but shale is particularly troublesome from that standpoint. There may or may not be a transitional or weathered zone in a particular shale deposit. It may be fissile or thick bedded. It can have highly variable strength. And it's not uncommon for it to be interbedded with limestone or sandstone. And you know, the local geology will dictate what you can do in any particular generally shale environment. And I know that's not very helpful from the standpoint of how you're going to attack it, but that's just the reality of the situation. There may be information available from drill shafts operations in terms of shaft resistance and drillability, but shales are a bit tricky from an intermediate geomaterial standpoint. A good place to start in evaluating shales is GEC8, and the section on shales is based on a 2005 paper by Vilpulamandan, who would ask that you call him VIP, but it was a load test funded by the Texas Department of Transportation, where they had 8 piles socketed into clay shale. Look at the unconfined compressive strength values from 1 to 30 TSF. a pretty wide range. But the good thing about this method, or the thing I like about it, is it looks at capacity in terms of pile head displacement. In other words, you plug in the parameters that you have in terms of unconfined compressive strength, and you select a pile head movement, and then out of this process, which is described in detail in GEC 8, you get a working capacity. So maybe it helps bring some clarity to the shale side of this intermediate geomaterial process. Russ, that's all I have for you. Do we have questions?
Yeah, Willie, we do have a couple questions. Let's see, the first one, is sand still typically being used in the grout mixes?
Yes, but it's ASTM C33 concrete sand. I gave that historical context just in terms of the development of the general auger cast in place pile process, and they did in the 50s and into the 60s mix the grout on site using masonry sand, which is very difficult to pump. So yes, sand is still used, but it's it's ASTM C33 concrete sand. And in that light, one of the reasons why cast in place piles have done so well in the Miami area is that there is sand available in that area, which is just absolutely perfect material. So they don't have any problem developing 5,000, 6,000 PSI in their grout mixes because of the nature of the sand that's available down there.
Okay, we had another one. What the Philly site, what type of load test was used in Philadelphia?
The load test that was used was the quick load method, and I'm having to. I was not directly involved in that, but that was it was a quick load method.
I think that was also tension and compression, right? Based on the plot.
Yes, there was a tension and compression test, and both of those were done using the ASTM quick loading procedure.
Okay. I think we have another question on that Philly test. Was the load test installed and tested at the basement level? I know the basement was okay.
Yes, everything was excavated down to that basement level, and that's where the test file was installed from.
Okay. Another question here. How should conventional pile capacity models be modified to account for this type of pile for more accurate predictions?
That's an interesting question, Russ. I would direct you to, again, Federal Highway Geotechnical Engineering Circular number 8, which was, this thing was worked on from, I don't know, 2000, 2001, up until the time it was published in 2008. And it involved a strenuous study of U.S. auger cast in place systems and European cast in place systems. And they tried to integrate some of the better processes of both systems into recommendations, but the capacity analysis processes that are described in GEC 8 for cohesive, non-cohesive, intermediate geomaterials, and displacement piles are, I think, the best source of reference for pile capacity analysis.
Thank you. Next one we had was how has your project load test compared with the Coe and Flume chart?
Okay. Well, as best, well, let's take a look at this slide right here. We believe, we think that Piedmont partially weathered rock or Piedmont altered rock operates in the general range of 2.5 tons per square feet in terms of load transfer for shaft resistance. And this piece of data from the 500 Walnut Street, if you look at the lower 14 feet, the implied load transfer is 2.65 tons per square feet. And the chart that I showed earlier from the Atlanta Piedmont area comes in at about 2.5 tons per square feet. So that's pretty consistent. And if you look at the Cohaue and Foon chart, it sort of makes sense. We're looking at the Piedmont coming in at 2 to 2.5 tons per square feet. The limestone in the Miami area is is again up the food chain a bit, operating more up to 8, perhaps 10 tons per square feet. So if you look at the material that we're talking about, intermediate geomaterials, something between hard soil and into soft rock, to me it makes perfect sense, which is why I use this Cohaue and Foon chart so religiously. The materials we're talking about fall really in the range where they are supposed to be, I think, based on this chart.
Thanks, Willie. All right, we had another question here. For the fixed mast rig, you showed the reach of about 2 meters. For greater distance, is it common to walk the rig over the piles constructed already?
Yeah, see, there's your problem. If you plan ahead, you can do that. If you, for example, you would, for a fixed mast rig in this kind of environment where you had steel sticking up, you would have to plan very carefully and work out the center of this pile group first, because if you started walking back over these piles with reinforcing steel sticking up, you would screw up the steel. So, and that's why I brought it on, because a lot of times when you're dealing with intermediate geomaterials, it seems very intuitive that you would go with a fixed mast rig, which has extremely high torque and the ability to crowd the tooling. But sometimes it's just not feasible because of the site logistics. So it's just, and don't get me wrong, I'm a fixed mast devotee. That's I love those machines, but sometimes the site logistics just don't lend themselves to using that kind of equipment. So the answer is no. You can't walk this rig through that uh, jungle of reinforcing steel to get to that pile area. You better put that pile in early in the game and then work your way out.
Okay. In your opinion, what is the most notable shortcoming or limitation for auger cast piles?
Well, that's a tough one. See, since I used to work for an auger cast pile installer, the answer should be there are no shortcomings or limitations. But uh, it gets uncomfortable in significant zones of loose sand below the groundwater level. The theory is that the piling leads are full of materials and they help support the side structure. But the reality is that if you have underpowered equipment and you have a thick zone of loose sand below the groundwater level, there is an opportunity to extract excess material. So to me, that's where you need to be careful in using auger cast in place piles.
Okay. Another one, any insight in relating what kind of refusal or penetration rate to look for when penetrating these materials, or specifically trying to predict capacity of the installation?
One of the issues, and most of my experiences have been in the Piedmont, or yeah, most of it. And one of the issues is the refusal level in the Piedmont is rarely level, plain. Well, it may be a plain. Oh, it's erratic. So one of the things that is normally done in a site where it is shown that refusal level is erratic is to do some probe piles and install a pile where perhaps you have the highest refusal level, and that refusal is often uh, given as 1 foot per minute of penetration. So when you cannot advance the tooling more than a foot in a minute, that is practical refusal. So a good thing to do would be to do some probe piles, find out what the refusal level across the site looks like, select a pile location with a higher refusal level and test it, and then maybe do another one with a lower refusal level. That's the way I approach the projects.
Okay. Yeah, Willie, I had a question for you. A lot of times you hear, questions about and necking of auger cast piles with soft soils. So how do you explain, or convince people that that's not something to worry about?
Okay, Russ. One of the things that came out of GEC8 and their studies in Europe, and the European system for putting in cast in place piles was totally different than the US. And the Europeans quite often used plastic concrete rather than grout. And one of the things that the researchers found was the grout take, excuse me, the concrete take, the overage for the European systems was much less than that of the US systems. And I think from my discussions with Mr. Berkel, they learned early in the process of developing cast in place piles. And Mr. Berkel said it often, grout is your friend. Don't skimp on grout. The grout oversupply is the primary factor in preventing necking or any uncomfortable sections in the pile. So in GEC8, there was a push to cut back on the grout take for piles installed using the US system. I mean, a European cast in place pile, the overage for their concrete might be 10%. You would rarely, if ever, operate at a grout overage of 10% in cast in place piles. It's usually 120, 120%, 130% is much more common. And that's not because the contractor wants to waste grout. It is just from the recognition that, as Mr. Berkel said, that grout is your friend, and that grout oversupply is your main tool for assuring that there's not a reduction in section in that pile.
Okay. And obviously there's a lot more instrumentation now that to tell you, how much grout you're pumping and if you slow the rate.
It's interesting. I guess starting in the 90s, maybe in the 80s, there was a instrumentation started to appear on conventional US cast in place piles, and it was all aimed at the grout supply. There was nobody really paid much attention to the drilling side. It was all the instrumentation was on the grouting side. Conversely, in Europe, all the instrumentation was on the drilling side, and the casting side just sort of took care of itself. So it's an interesting contrast of how these two systems developed. The European system, the idea was to try to drill in a way that at least maintained the state of stresses in the soil adjacent to the pile, if not improve them. On the US side, the idea was to make a hole in the ground as quickly as you can and fill it up with a lot of grout. And that's just the reality of the way the systems developed.
Okay, thank you. And actually, one other one was just, would you be okay with distributing the slides in PDF to the group?
Yes, I have signed a document that allows DFI to own this presentation, and I assume that it could be made available to whoever would like to have it. I'm unsure about that. All I know is I signed a document that said this is in the public domain. So yes, the slides and the accompanying notes. If that can't happen through the DFI, I will send it. I will send it to you in PDF form if you want.
Okay, great. Actually, we had just one more question just pop in. Is there a latest technological advancement in the development of deep foundation system, of this deep foundation system? I guess any latest development, trends for ArcGIS files?
The slide that I showed with the crane mounted rig where the contractor had taken a turntable from a fixed mast rig because it had higher torque and mounted it on a set of swinging leads is an example of where advancements are going to come from. And it is the contractors because they are the people who have that let's face it, they have the most to gain by doing something better or faster or cheaper than the other guys. So that's why I don't want to harp on DFI, but that's where designers, geotechnical engineers can sit down with contractors and talk to them about what they're doing and how they're doing it and the pluses and minuses of it. So the advancement and it's not only the contractors, but also the equipment manufacturers are just making bigger, stronger equipment that's able to go deeper than it did before. And the industry is changing terribly rapidly. I mean, it's really difficult to keep up with the equipment manufacturers and the contractors who are doing things that weren't possible to do 10 years ago. So I don't know if there is a single thing that I could point to as an advancement in the industry, but I can tell you that there are contractors right now who are going to bed programming themselves to dream about what the next best thing they can do might be. And equipment manufacturers are the same.
Okay, I think that was the last question from the group. So thank you very much, Willie. That was an excellent presentation, very informative and very relevant for the Philadelphia area. I want to thank everyone else for sharing their evening attending this webinar. I hope everyone has a fantastic summer, and hopefully we'll see each other in person in the fall. And Willie, I hope I meet you at a future DFI conference since we didn't get to meet.
I'm a big fan of blackjack. So if I could attend a meeting at the casino in King of Prussia, that would be just wonderful with me.
It's right right downstairs or right across the hall. So yeah, we missed out.
Okay.
All right, everyone, have a good evening. Thank you very much.
Thanks, Russ.
Okay.